Hi, hello everyone. Good afternoon after the whole day of the conference. I guess you already ingested quite a lot of interesting knowledge, so thank you so much for showing up here at the end of the day. My name is Tomasz Tarczyński. I work at Isovalent. My role there is a customer reliability engineer. So what I do as my day job is basically helping customers running Cilium in production, making sure that they have their experience is that Cilium runs as reliably as possible. So what I want to talk today is day two operations for Kubernetes networking and how to do that with Cilium. Let's get started. So first, you might have an experience like that, working with Kubernetes, deploying stuff on Kubernetes, being happy that it all works, but then raise your hand if you ever felt like this. Trying to learn about Kubernetes networking, seeing how much complexities is there. I mean, myself, it took me years and years to get at least some reasonable understanding of how it works, and there is for sure still a lot more that I still don't have a really deep understanding. So we will start with introducing Kubernetes networking, just very briefly, then talk a little bit about what I mean by day two operations, then thinking about Cilium networking, Kubernetes networking in general, but then with the Cilium focus as well. What are the important design decisions? And the last bit would be about observability. So let's get started. Thinking about Kubernetes networking, I wanted to start, take even one step back and start with how traditional networking looked like. So back in those old days, you tended to run your applications statically on a given node. Then you gave them static IP addresses. You assigned those to the nodes. The routing protocols, you might have dynamic routing protocols, but it still didn't change a lot. And then what are the important networking topics that you needed to take care of when running distributed systems? So one thing is connectivity in the east-west direction, so between different applications within your data center. You needed to have some way of service discovery. A very simple approach would be just a DNS server. There are more advanced options as well, but let's keep it simple. And then the north-south connectivity. So it goes both ways. Your applications might want to connect to the outside world, and similarly, your end users would connect from the internet to your application. So you need to plan for that. For example, with stuff like layer 7 load balancers or a reverse proxy. And of course, you want to make this network secure. For that, you would use stuff like firewalls. You might do encryption of all the traffic, even inside your data center. And then you might require your applications to authenticate to each other and to get authorized to access each other. So that's my just 2-minute intro to how traditional networks look like. Was it simple? You might think that it's simple, but that's my teammate, Piotr. So he's doing this stuff for 20 years, and that's his bookshelf of his networking books. So if you go deeper and deeper into those topics, even traditional networking, it's, I would argue, not an easy thing to grasp. And now let's enter Kubernetes. So our cloud-native world. Topics are the same, but we approach them slightly different. And I would argue the very most important difference here is that everything now tends to be really, really dynamic. So we run our applications in pods. Where they exactly run, we don't really care so much because it's all dynamic. So somewhere on those hosts, but we don't know anymore where exactly. They do have IP addresses, one per pod, but it's also happens automatically, dynamically for us. Thus, routing connectivity between those applications, it needs to happen dynamically as well. Of course, it's not just magic everything, like those packets needs to get from point A to point B somehow. So you can still see this underlying network below our Kubernetes cloud, so it still needs to connect somehow. And then the topics I mentioned before, they still apply here. So applications are connecting between each other. For that, for east-west connectivity, we typically use services. So that's Kubernetes abstraction for connecting applications. But we might also go a little bit more advanced, do stuff like service mesh or gateway API, also for that. We need service discovery. We have the DNS service within the cluster. And we also need this north-south connectivity. For that, we typically use either the load balancer type of a service or stuff like ingress or gateway API to control not only traffic on layer 4, but also to have layer 7 controls over the traffic going to the cluster. And we also do have our security needs. So we want to limit which application can talk to which one. So we use network policies for that. We might want to encrypt our traffic with transparent encryption. And we might want to require our applications to authenticate to each other. I've also put where those things can be done in different components in our cluster. Let's see a summary of that. So we have different components different networking components in Kubernetes, and what their roles are, just those things that I've just talked about. So CNI would be responsible for IP address management, routing, and also security. And then we've got kube proxy for the services, DNS for service discovery, ingress for north-south connectivity, and then stuff like gateway API addressing similar needs to ingress, and service mesh to have even more fine-grained control over all of our traffic. So when I think about Kubernetes networking, that's pretty much the landscape that I have in mind. Let's then dive into the data operations. Because from my experience when working with customers, the users who run this in production, they really, really care about those considerations, like how to make sure we are successful for the long term. To start with, who has ever seen this quite an old thing, the 8 fallacies of distributed computing? That's something that came from Sun Microsystems 30 years ago. So they were trying to reason about what are the important characteristics of distributed systems. And they observed that engineers pretty much invariably make those false assumptions. And the assumptions are, number one, that the network is reliable. People tend to assume that. Stuff like latency is 0 and bandwidth is infinite. Basically, if we run network distributed systems long enough, we then learn the hard way that all of those are false. They are all not true. Going further, people assume that the network is secure by itself, that the topology is static, it doesn't change. There is one administrator. That's one of my favorites because it assumes that there is just one person who makes all the decisions about this network, which is typically not the truth. You would have multiple teams designing and running those things. And then transport cost is 0. In the cloud, yeah, you can learn this, that it's not true the hard way as well. And the network is homogeneous, so it assumes all the segments of your network would behave exactly the same, which you can learn it's also very often not true, or typically not true. Okay, so what considerations would I recommend to keep in mind when planning for your, let's say, production Kubernetes story, how to design your network, what decisions to make? So first one, reliability. It cares about stuff like defining your service level objectives. How would you measure what does it mean that the things you run, that it runs well? Stuff like availability of your components, which might be not such easy to define like in fine-grained manner. Performance, what are your performance expectations? So those things that we just talked about, like latency, throughput, stuff like that. What are the typical failure modes? So how your components can break. They will invariably break sooner or later, but that's good to think about it in advance. What happens, let's say, what happens if your Kubernetes API goes down? It's not available. How it affects all of your networking components and what functionality will be broken there, what would still work. And then troubleshooting tools. With traditional networking, you had your TCP dump, you had your observability there, and things were quite straightforward, let's say, or way more straightforward. And now it's way more difficult. Looking at a TCP dump in Wireshark, it doesn't help you much because those IP addresses don't make much sense. Like you can't easily know which IP is what application. And then planning for long-term maintenance. So what kind of support you need for all those components for your network? Are you supported by your cloud provider? Does it include each and every component there? Or do you use third-party components? And then what kind of support you need? Or like, are you happy with just being supported with the open source community, or you want something more? How would you plan for upgrades and the possible deprecations? Like some functionalities might be discontinued, or even some projects might be discontinued. Probably difficult to plan for that, but something to keep in mind that might happen as well. Thinking about performance and scalability, it's mostly like the two factors I already talked about. Then trying to plan, like, are you well prepared to run at the scale that you need? There is Kubernetes 6 scalability that discusses those topics. One of my colleagues at Isovalent is leading that 6 scalability, and the one of the things they do is they define the service level objectives for Kubernetes. There are many different parameters there, but among them there are the networking params as well. So they ask questions like, what is the latency in your network for programming it? So when you add a new application, a new pod, how much time it takes for your whole cluster to converge to be able to route traffic to that pod. What is the ping latency? So just sending a request from one pod to another. And similarly, for kubedns, the same thing. How much time does it take to program it when you change definitions of your services? And how much time it takes to do a lookup. Those things are among the topics that we see that the Cilium end users care about a lot. And when things go wrong, it's something they really want to troubleshoot. And yeah, that gets really, really important. Like you would probably don't think about it when everything goes smoothly, but those things are, yeah, sometimes fragile as well. Security. So the first layer of security in Kubernetes, that's network policies. They are identity-based, so you no longer define your firewall rules by IP addresses, but you rather want to define which pod, which workload can talk to which other workload based on labels. And those can be defined on layer 4 or as well on layer 7. That depends to like what exact decisions you make, what components you choose. You might also want other things. You might want to do transparent encryption, to do mutual authentication, or even zero trust networking when application will not answer the request unless it's all encrypted, authenticated, and authorized. Yeah, and you can achieve those things with different components in your cluster. Observability, yet another day 2 topic. And I would argue that I view this one as probably the most important for the data operations and for your long-term reliability story. Because if you can't observe something, it's really difficult to reason about how well or how bad it runs. And yeah, the Kubernetes networking model, it changed quite a lot for networking observability. The typical questions here are, how can you observe your network flows? I mean, not only seeing a graph, how many requests have hit the application, but actually being able to see each individual request going through the network and being able to follow it. Then there are network policies, and you would like to have some visibility for that as well. Also in form of graphs, but also in form of flow logs. And also here, it's observing the health of your components in your network. So saying visibility, I mean logs, metrics, alerts, and tracing. All those things are really important to think about when planning that. And the last part, the human factors. So that's also important not to forget. And especially, I would focus on the first 2. So we saw the whole landscape of the Kubernetes network. There are quite a lot of different things, and there can be quite much complexity in it. Depending on how exactly you implement it, it can get complex and can get quite overwhelming for people running it and people using it. So that's also something important to think about the cognitive load of people working with those systems. And other stuff, it's like, for example, cross-team communication. There might be multiple teams dealing with your cluster or even operating it. Also thinking about human error as well. Okay, let's now jump straight into the design decisions that I would say are really important to make when planning for your production setup with Kubernetes network. So we talked about how the networking model looks like. And now building on top of that, I would like to focus on one of the components, the CNI. CNI, it's the container network interface. So that's a standard API defined by Kubernetes. It deals mostly with two important topics. One topic is that each pod in Kubernetes should have its network configured and IP address assigned. Let me jump here. So CNI takes care of that. It assigns IP addresses to pods. And then the role of the CNI is also to make sure that connectivity works between those pods. How this is implemented? It's done by the CNI plugins. You can choose among those. And they take care, apart from the IP address management, also about routing. So how this connectivity is actually implemented. We will look into that a bit more in a moment. So when you're choosing your CNI, there are quite a number of different options. And yeah, I would say for quite some time it was not an easy decision to make. Like when you studied for your CKA, you saw Flannel and Calico there as two options. One of them had network policies support and the other doesn't. But how it looks like today, I will not talk in detail about the different CNI plugins. Also, obviously, I wouldn't be objective discussing that, as I know one in very detail and others not so much. So just the information from the CNCF landscape. Those are the 6 most popular options, and people tend to choose between those. But also, if you run your cluster in public cloud, then your public cloud provider, they made some decisions for you already. So you set up EKS cluster, there's already Amazon VPC CNI. In GCP, you have the new option powered by Cilium, but also the legacy option powered by Calico. And similarly in Azure, the newest option that they have is powered by Cilium, but they also have their own older Azure CNI with optional Calico network policy support. And those providers, they also let you choose your own CNI. It differs from one to another. So for example, AWS, they specifically list the 4 Amazon partners who they also recommend that you can choose between. In Azure, you have an option to bring your own CNI setup and then configure whatever you choose. Okay, so that was about like the options you have, but now what's the architecture when you decide to run Cilium for your Kubernetes network? Very, very briefly, because it's not the topic of this talk. So what's important is that Cilium CNI runs on each and every node in your cluster, and it uses eBPF, which means it can program the Linux kernel to run all the networking logic there with identity-aware routing, with network policies and all the Cilium features, without going through the traditional Linux networking stack, which gives you really, really vast performance benefits. Yeah, that's a comparison between the traditional implementation with IP tables and Cilium implementation with eBPF. And yeah, with IP tables, the implementation of stuff like services, it required linear scaling, going linearly through the list of IP table rules in the table, while eBPF implementation, it uses hash tables for fast lookups and yeah, mapping your identities to the detailed networking rules. That's how Cilium runs, how it works. So the agent needs to talk to kubeAPI server. It watches a bunch of different resources there, and based on that, it programs your Linux kernel to basically program those networking rules in the kernel. Okay, so designing how to run Cilium, what are the decisions you would be making? First one is about what type of routing you want to use. And there are two high-level options. First is encapsulated routing. So to make connections in between nodes, and those nodes might live in different network segments, Cilium would create VXLAN tunnels between each and every node. It basically encapsulates your network packets in UDP packets. What are the advantages of that? It's a really simple approach, like it will run practically everywhere. The only requirement is that you need to have UDP port or 8472 open on those nodes on firewalls, and that's it. It gives you a possibility to have really large address space for your pods. It's configured automatically, the default mode in Cilium. It also has a disadvantage, so it adds an overhead for your MTU. So this encapsulation will eat 50 bytes of your network packets. And then there is the other option, which is native routing. So here we are using the underlying network to take care of routing in between pods in your cluster. To make that work, what needs to happen, we need to configure the routing tables on all the nodes so that the nodes are aware how to route traffic to pods on all other nodes. And similarly, the underlying network also needs to have the knowledge of this network topology and how to route. What are the advantages? There's no MTU overhead anymore. You don't need to do source network address translation when going outside of the cluster. Your performance could be a little bit better. And there is a disadvantage. So the most important is that there are those requirements for the underlying network. Plus, and because of that, the underlying network requirements, it might get more difficult to set up. And the second very important design decision, it's about IP address management. So there are multiple different modes, different options for that. I will not go through them in detail, but that's something you definitely would need to plan for. In most cases, I would say the approach I would propose would to be go with the default mode, so cluster scope, which enables you to run either encapsulated routing or native routing. But there is a caveat to that. If you run in one of the cloud providers a managed cluster, then I would say it's way better to choose one of their IPAM provided by those cloud providers. And each of them has their own thing, and you would run native routing then. Okay, so to end with, as we are running out of time, so yeah. Just to take a very short look into the whole networking landscape in the cloud native CNCF landscape. So we talked about all those needs in terms of networking, and just looking briefly how we can implement each of those. For the CNI, you can choose to use Cilium for that. Then you have this east-west, north-south connectivity implemented typically by kubeproxy, but there is an option to replace that by Cilium as well. If you need an ingress controller, Cilium can cover that too. Similarly for gateway API, and similarly for most of those service mesh functionalities. But a caveat to that would be, I wouldn't recommend to start with everything just at once. Thinking about the typical journey of people implementing those different topics, those different needs, I would argue that perhaps a better, more sensible approach would be to start here. So if you can, you always need to choose a CNI. So I would say put Cilium there, and then I would say the second topic would be to focus on observability. Okay, as we are running out of time, I will not go through the observability demo that I had here. So apologies for that. If you want, you can catch me here during the conference. I can still show you what I have prepared there. And what I would recommend instead is you can play yourself with all those things. So we have a really vast library of Cilium labs where you can learn all those functionalities in hands mode style, especially those related to observability, so the golden signals with Hubble and flow visibility with Hubble. And that's it. So thank you very much for listening. Do we have any time for questions?
We have 1 minute. So is there any question? And I would say no. So thank you very much.
Thank you all.